service new into the damping effect. Then actually we applied the Laplace transform for this thing. Then we divided this equation by L delta of this. This delta term actually got vanished. Then we were only left in this equation. Then that can be compared with the second order dynamic system. Okay. And by comparing this with this technique, we actually calculated the only time, that is our natural frequency of oscillation, and the theta of the damping ratio. Then we actually saw the effect of H and PS on the values of theta and omega, as well as we actually observed the effect of PS and damping on the stability. Okay, so this slide was very much important. So if our PS is the synchronizing power coefficient or the slope of the power angle curve. If this thing is negative, okay, then actually irrespective of the values of G and theta, the system will be unstable, right? Because once this PS is negative, we do not need to bother about the values of G and delta. It will be in the unstable region. And this is the time domain response during the process T. You can see over the time the delta value is increasing, right? And the second case, the PS is now positive and the G and theta is 0. That means we haven't incorporated the damping in our system. That was the first case of this slide, right? Whenever there was the damping. In this case, the system will be marginally stable, and we are getting two poles along the y-axis. And the marginally stable means the delta will be swinging between these two fixed values. It will neither decay nor grow over the time. And the third case, if the PS is positive as well as if the G and theta are positive, at that time the system will be stable. What does it mean by stable system? So it will try to, if you continue this simulation, you will see that it is reaching to a final value, right? This is a stable case. And if the damping is negative, so the system will be unstable. Okay. Now,
Sir, if T is negative, then why you don't need to bother about P and theta?
so once actually the PS is negative, that means let's go back to the previous slide. So this is the PS case, okay? And this is the case without damping. So in this case, we didn't consider the damping effect. So this is the power angle curve T versus delta. It will be between 0 to pi, and at pi by 2 we are getting the maximum. From 0 to pi by 2, the slope is positive. The slope is represented by this PS. That means the PS is positive. This is our stable region, actually the marginally stable region. To discuss this thing, whenever PS is greater than 0, this is the marginally stable, right? But once we go beyond this pi by 2, our slope will be negative. So beyond the PS is negative. Okay? PS negative means look, the system is unstable because one pole will be in the right side of the plane. That will make the system unstable. Okay? So this is actually the unstable region. That's why we can go from 0 to the maximum pi by 2. That's why that pi by 2 was more or less the steady state stability. So this is our unstable region. So if the PS is negative, at that time do not think about the G or T. If you impose G, positive T or negative T, that will not make the system stable because it is actually the unstable region. Okay. That's why here in this table, the first case is the PS is negative. That's why the G and theta values are drawn here. That's that will not need to bother about that. Irrespective of these two values, we will get the system is unstable. Okay. Now, we completed up to now in the last class. So, and I actually told you that we actually took help of this Laplace transform due to the convenience, so that we can easily solve the problem. We can observe the stability status of the system, right? That's why we took help of the Laplace transform. But we, up to now, we haven't given any mathematical expression in the time domain form, right? So that's why again from this Laplace domain, we have to go back to the time domain mathematically. How? We have to apply the inverse Laplace transform, right? So this is our equation. We have to apply the inverse Laplace. Okay. Look here. By looking at this equation, can you say what is the main variable of interest here? In this equation, it is del delta, right? But whenever we apply the Laplace transform, we divided this del delta, and actually it got vanished. Can you see? There is no del delta, but that was our main variable of interest, right? And we have to just discard it. Why? Because actually this is the way to solve the Laplace transform for any x, either it is in the electrical domain or mechanical domain. Whenever you solve the Laplace transform, you actually in the first hand you actually discard the main variable, okay, and then you just play with the s values, okay, and your first target is to observe the stability status of the system. Once you know that the system is unstable or stable, again you apply the inverse Laplace from this equation and you find the del delta of t, that is your task. Okay. So now we have understood actually how the system will be unstable, marginally stable or stable. Okay. Now again, using the inverse Laplace transform, we have to find the del delta of t, so that we can understand the time domain response. Because these are the figures that you can easily understand, right? But you do not know these initial values, right? These values you do not know. Also, you do not know these values, that means the it will be settled down, right? So how you will find this value? So you have to get some mathematical formulation, right? That's why we will now apply the inverse Laplace transform. But before that, we have to learn a new topic that is called the state space model. Why? Because actually this model gives us the dynamic behavior, okay? Dynamic behavior or response of the system. That is with multiple inputs and outputs. Okay? So if there are multiple inputs and outputs in our system, so to observe the dynamic behavior of the system, it's better to represent the system in state space model. Okay? And whenever we will just do the inverse Laplace here, we will see that there are multiple factors that is working here. Okay? So that's why it's better to represent the system in the state space model. Okay? That's why today actually we will learn about the state space modeling and we will learn how to form this state space model. Okay? In the first case, as we are not familiar with this topic, so I have heard that in your control system, this topic has been skipped, right? You haven't learned it. So that's why in the first case, we will try to understand the concept using a very simple example, that is the RLC series circuit. Okay? That is obviously out of our syllabus, right? This topic. But we will see the state space modeling of this circuit so that we can understand the thing very easily, right? Then we will apply the state space model for our linearized single machine infinite system. Because this is our system of interest, right? So before that, we need to understand the concept of state space model. This is the general form of any state space model. This dx over dt equals to ax plus b. Okay. So what is actually the x here? X is the state vectors. Okay. All the explanation of these parameters are given in the next slide. No problem. Okay. I'm just trying to give a recap. Okay. So x is the state vector that will contain the state variables. Okay. So let's say we have n number of state variables in our system. It can be only one state variable or more than one. If we have n number of step variables at that time, what will be the size of this x? It will be a vector, right? So the size of this x will be n by 1. Okay. Also this is the same x. This is n by 1. Okay. Now in the left side, this is x. The size of the x is n by 1. So what will be the size of this thing? The derivative of x with respect to the time. It will be the same size, right? Let's say inside x you have x1 and x2, two values. So if you use this format, it will be dx1 over dt and another element will be dx2 over dt, right? So the size of the left side term is n by 1. Now this x is also n by 1. Now can you say what will be the size of this a, so that the matrix multiplication can be done, as well as the left side size can be used. So what will be the size of this a? Exactly. n by n, right? So that this, obviously this n and this n should be equal, right? And why this n? So that the product of this a and x can be the size of n by 1, right? Now this u is the input vector. Okay, u is the input. Let's say for this system, this VIN, this is our input. There is only single input, but there may have multiple inputs. Okay, so this is the input vector. Let's say we have m number of inputs in our system. So the new size will be n by 1. Okay, this will be a column vector of size n. Again, using the same concept, can you say what will be the size of this b? If the size of the u is m by 1, what will be the size of b? M by n. N by n. It will be n by n. N is clear to you because the row of the second matrix is m, so the column of the first matrix should be m, right? And what will be the size of the row of this matrix? It will be m. Why? So that after multiplication you can get n by n. That is exactly equal to your left side, right? So if the product matrix has n by 1, if it is n by 1, then you can add this two. Finally you will get a n by 1 matrix at the right side, right? So using this concept, you can easily determine the size of the matrix of A and B. Okay. Now let's focus to this example. So this is our D of the input that will inside the system. Okay. So it has different things. You can see call it as input. You can call it as excitation. Okay. Or you can call it as forcing function. Okay. Because we are in the now transient response or dynamic response instance. Okay. So we will try to observe the transient or dynamic response. Okay. So in your circuit 2 course, you have heard this type of terms, right? Forcing function. Right? So you can say this VIN is the forcing function. Okay. Now just apply the KVL and write this equation. What will be your VIN? It is simply VR plus VL plus VC, right? Now what is VR? So current across these three limits is I, right? As this is a series circuit, so the same current will be flowing across these three limits. So the VR will be I multiplied by R. And what will be the VL? It is L VI by dt. So there is one interesting point here. We are studying the dynamic behavior of the system. Whenever someone asks you about the VL, okay, you just by default your brain just tells or answer this thing that it will be L VI by dt. But this is only true in the dynamic state, in the transient state. But if it is in the steady state, what will be the VL? In the steady state, what will be the VL? Okay, so again you are confused between the steady state and the DC. And you are talking about the DC input scenario. The input is AC, and for the AC input you can have the steady state scenario or the transient state scenario, right? a steady state scenario, how you can represent the VL? So let me make the things easier for you. Let's say this is a impedance, okay? Let's say this is a combination of resistance and the inductance of it. So how can you represent the Z? It will be R plus JXL, right? This is the representation of impedance. That means we have the resistance here and we have also the inductance L here, right? Now, let's say the current I is flowing across these two units. So you can write here, that is the voltage drop across the resistance as I multiplied by R. So what will be the VL? Can anyone say? Exactly, it is I with this term, this imaginary term. It will be simply I, J, XL. Okay, and XL can be again given as I, J omega. Okay, I think now you can recall this thing, right? In some of your previous courses, you have found this thing, and for capacitor it will be divided by 1 basic, right? Like this. Can you recall this thing right now? This is for the steady state response. But here, obviously, in the state response modeling, we are focusing the dynamic behavior of the system. That's why the VL will be LVI by dt. Okay, that is the current dynamics. Across the inductor is captured using this equation. Is the VL equals to LJ by dt. Okay, so what is the dynamic behavior here? So the dynamics of the currents, right? Across the L is represented by this VL. And plus now VC. Let's keep it as it is. We will deal this VC separately in the next slide. Okay. Now, what is your general expression for the steady space modeling? It is dx over dt, right? In the left side. Okay. So this dx over dt you can write it like x dot. It's okay. Do you know this thing?
Yes,
This
sir.
x dot means the first derivative, right? With respect to time. So this is your actually the general expression that I have written here. Instead of dx over dt, you can write simply x dot. And in this side, it is ax plus du. Now, we have to match this equation like this expression. So you can see in the left side, you will only have the d over dt term, right? So that's why you have to take this term in the left side and other terms should be in the right side. So if you bring this thing in the left side, it will be this thing. And let's say this IR and VC, you are taking it in the V inside. That's why it is minus IR minus VC plus V. Okay. So there is L here, but there is no coefficient here, right? The coefficient is 1 here. That's why you have to divide this equation with L. Then you will get 3I over dt equals to minus R by Li minus 1 by LVC and this is plus 1 by LV. Okay, have you understood this thing? Now let's deal with the capacitor current. What is the capacitor current I in the dynamic state? It is C dV over dt. V is the DC, the voltage across the capacitor, right? Now you can write it like this because you have to express the equation like this general expression, right? That's why it is simply d dc over dt equals to 1 by ci. Okay. And let's say this is another equation. The resistive voltage drop in the that it is equal to IR. Now we have to find out the number of state variables from these equations, and we have to also find out actually what are the state variables. State variables will be inside this X. It will be a column vector with the size of n by 1, right? So n is the number of state variables. So how we will identify the state variables? Easier way is that you have to look at the d over dt term. Okay, so you will look at the d over dt term. So how many d over dt term is they are present in your system? That will be the amount of your state variables. Okay, so how many d over dt term is here? your x. Okay. Then what will be your x dot? It will be simply your di over dt and dc over dt, right? Now you can write it like this. Okay. In matrix form, it will be x dot equals to ax plus b. Okay. You know the x and you know the x dot. So just place the x dot here and place the x here. I is. So these two unknown to you. Okay. Now you have to look at these two equations. This is your equation number 1. This is your equation number 2. And you have to fill up the entries of the A matrix. Okay. First you have to calculate the size of the A matrix. So this is 2 by 1. This x is 2 by 1. So what will be the size of A matrix? It will be simply 2 by 2, right? So that the product can be 2 by 1. Okay. So now you have 2 by 2 matrix. So you have 4 entries, right? You have to just place these entries. How? Look at these equations. This is di over dt, right? It is minus r by l I. So look, if you just use the concept of the matrix multiplication, this first row will be multiplied with this I and bc, and you will get the di over dt, right? That means this first element will be multiplied with this I. So you have to place here minus r by l, right? So that you get minus r by l I. Then plus this term multiplied by this, right? So that is minus 1 by l bc. So that's why you have to write here minus 1 by l and multiply this thing, you will get minus 1 by l by multiplied by bc, right? Now there is some additional terms, right? That is what p. Now what is u here? Only the p, right? There is no other input here. So the size of the u is 1 by 1. So what will be the size of p? It will be 2 by 1, right? So that the product can be the size of 2 by 1. So now you can write the u. U is only the p in. So you know the u. You know the size of b, but you do not know the entries. So you have to place the entries here. Okay. So what will be the first entry? Look, it will be multiplied with p in, and it will give you the value of di by dt, right? Look, for the di by dt, that is plus 1 by l b. So that's why you have to place here plus 1 by l, right? So this is the thing. Now for the second equation, it is d dc over dt, and it is simply 1 over c multiplied by I. That's why the first element will be the first element of the second row will be 1 by c, so that it can be multiplied with this I, right? And the second element of the second row will be multiplied with the vc, but there is no vc associated term in the right hand side of the dvc over dt, right? That's why it is simply 0. Okay. And for this case, is there any input dependent parameters in this expression? No, right? That's why simply this is also 0. Okay. So I think this is easier to do. You can simply do this thing. Maybe I am explaining too much, right? But have you understood the point how actually we can express this thing in matrix form? Okay. So now this is your h dot equals to ax plus b, and you have found out your a and b matrix. Okay. Now let's go to the next slide. So what is the name of the x? X is your state vector that will contain the state variables. Okay. For this example, we have I and bc. You can term it as x1 and x2 because there are two state variables. What is a? A is called the state matrix. This is your a for this starting example. Obviously, there will be different a for another example, right? So this a is not fixed. This b is the input to state matrix, because this b is associated with this u, okay, and your u is the input vector, okay. And this equation is x dot equals to ax plus b. This is the your input equation, okay. This is the input equation. Now, if you wish, you can also write some output equations, okay. And for the state space modeling, your output equation expression will be this. This is your general expression for your output expression. Y is your output, x is your state vector, u is your input vector, and again c and d. Okay, using some intuition and concept, you have to formulate the c and d, right? Again, How? Look, let's say you are actually taking the VR as your output, and this is the choice of the designer. Okay? You can take VL or VC or I as your output. That is up to you. Okay? So this is up to the designer, because designer is at the output side. Okay? So let's say he or she wants to control the system. So the output that he wants to take, that will be his choice, right? So if another designer wants to take other output, he can take. Okay. Now let's say for this specific example, we are assuming that the designer is taking VR as the output. So this is simply the Y. Okay. So what is the size of this Y? Simply 1 by n, right? 1 by 1. So and you know the size of X. It is the same as before. This is 2 by 1, right? So what will be the size of the C matrix? You know this thing. It will be simply 1 by 2, right? So that this 2 and 2 can be vanished and the product size can be 1 by 1, right? And you know the input. There is only single input V. The size is 1 by 1. So also the size of the D matrix should be 1 by 1 for this output, right? Now you know the VR. What is VR? You have to write the expression. This is simply I multiplied by R, right? So you can write the X. How you will write the C? So this is the VR. You know that the first element will be multiplied with the first element of this X. So that's why you have to put R here, right? And this will be multiplied by this. So there is no VC term. So there is CC. Plus, is there any input term here? No. That's why this D matrix is 0. But obviously, always this D will not be 0. If that's the case, then there is no point to introduce the D here, right? For this particular output, we are not getting any D here. But maybe if you take VL or VC as an output, at that time maybe we will get some G, right? So this is your output expression, and this is the general form. Cx plus G. Okay. And what is C? C is the R 0 and D is the 0. This Y is the output vector and C is the output to state matrix. Okay, and your G is the output to input matrix. Also, you can deal with multiple outputs at the same time. Let's say you are to take your VR and VC as your output. Okay, you can do that. At that time, the size of this will be 2 by 1. Then accordingly you have to choose the C matrix, right? Plus G. You know the X, you know the U. So by looking at the equations, you have to write the C and D matrix. That is the thing. Okay. Have you understood this thing?
So what was D?
Yeah.
What was D?
Okay. So D is associated with this input U, right? That's why it is called the output to input matrix. Why output? Because this D is for your output equations. So output to input matrix is called. Okay. And this C is output to state matrix. Why output to? Because this is the output equation. Why state? Because look, this C is associated with your X. S is your state vector. That's why it is called the output to state matrix. Okay. This is the output to input matrix.
Why was D suitable?
Here for this, because you are taking VR as your output, right? So what is your VR? This is IR. You know this thing. So this U is the V. So what will be your G here? You have to write 0 here, right? Because there is no V in term. V multiplied by 0 here, right? That's why this is 0.
So if we take D and D matrix formula to
Yes, you can easily formulate it by yourself. Okay. I'm not showing it here because this is our example of RLC series certificate that is out of our syllabus. And we are not focusing about this example. We will go to the CPU machine defining impulse system, right? But just in this two slide, I am just giving you the idea of how to express the input equations and the output equations of the express system. Okay. You can do it by your own. There will be two equations. One will be for VR, another will be for VL, right? You will get some equation for VL. So you can formulate this C matrix as well as the D matrix, like we did in this case. Okay, there was two inputs, so we formulated the A and the D matrix. Here also you can formulate it. Okay. Now any questions on the state space model for linearized single machine infinite mass system. Okay, so this is our we are now in our system. Okay, now we will just try to relate this concept with our previous concept that we just started. Okay, so that you can just understand why actually we have studied this topic out of nowhere. Okay, just we will try to relate. So we are rewriting the second order linearized swing equation. So this is our second order linearized swing equation, right? Obviously with damping, because this term is coming into the damping effect. Okay, and this is the now. Now the first step is to find out the x, to find out the state vector. Okay, and we have to find out how many state variables are here. As the system is second order system, so we can easily say that we will have the two state variables. Okay, so the number of state variables will be 2. But what are they? How to identify? So in the previous example, I have told you that you have to just look at the d over dt term, right? And look, there are two d over dt terms, one is here, another is here. That's why your I and Vc were the state variables, right? Similarly here also you have to look at the g over dt terms, right? So can you say, let's say we know that we will have the two state variables because this is the second order system. So we will have x1 and x2, right? This will be your x. And what will be your x dot? It will be simply x1 dot x2. That is the dx1 over dt and dx2 over dt. Okay. Now we have to find out what is x1 and what is x2. So can you say we have to look at the d over dt term, right? So this is one d over dt term. So what will be the state variable from here? It will be del delta, right? So look, our x1 is del delta. Okay. Have you understood this thing? Now, what is our another d over dt term? Okay. I said you the d over dt term, not the d square or d cube over d cube term. Okay. So we have to look at the d over dt term, right? So this second order term we can split it like this: d over dt, d del delta over dt. Can we write it like this? Okay. So now, what is our second state variable? This term as a whole, right? Because this is with this d over dt term. Okay. Now this is our second state variable. That is our x2. That is d del delta over dt. And it is nothing but the first derivative of our first state variable. That is the x1. That's why x2 is nothing but the x1 dot. Not the x1 is del delta, the del delta dot. That is the d del delta over dt. Okay. For this type of higher order system, you will get the state variables like this manner. That means if the order is 3, at that time you will get your x1, then your x2 will be the first derivative of your previous state variable with x1 dot. Okay, and your x3 will be the x2 dot. Okay, like this. Maybe you have seen this type of phenomena in previous of your courses, right? Have you solved this type of equations previously? Maybe in some of your math courses or in your Calculus or Fourier topic. Okay. So as the order of the system is 2, so first state variable is x1 and the second one will be x2, that is the x1. Also from this thing we can easily understand that this term is the second state variable, that is the d delta over dt. Okay. And we can represent it by del omega, right? Because this is the rotor angle and the first derivative of the rotor angle will be the angular velocity, right? And here the angle, this rotor angle is some small change in rotor angle. That's why we are getting some small change in the angular velocity. That's why we are introducing the real here as well, right? Now this is your x1. Now we can write what is our x1? Del delta, right? And what is our x2? d del delta over dt, right? This is our x2. Now we also have to formulate the x dot. That is our x1 dot and x2. So we need to know the x1 dot and have already found the x1 dot, that is simply the x2, right? Okay. So now we have to calculate the x2 dot. So what is actually the x2 dot? Look, this is your x2, right? x2 dot means the first derivative of this term. That will give us actually this term, second derivative, right? Have you got the idea? So this is your x2, and what will be the your x2 dot? The first derivative of this term, that is again this thing, that means this thing, okay? So that means your x2 dot means del omega dot or this term, e square del delta over dt square. Because del omega dot means the first derivative of the omega, that will give you the acceleration. The acceleration means the double derivative of this derivative, right? So what will be this thing? This two term you can take it to the right side, so you will get minus pi f naught t h t del delta over dt minus pi f naught ps over h del delta. Okay. Now look, what is this thing? This is nothing but your x2, right? So this is your x2. And what is this? This is your x1. So now you have found your x2 dot as minus pi f naught t over h x2 minus pi f naught ps over h x1. Okay. Have you got the idea?
স্যার একটু রিপিট করা যাবে? একটু রিপিট।
So first we have found the values of x1 and x2. So x1 is del delta, x2 is t del delta over dt. Okay. Now also we have found the capital S dot. That will be the x1 dot and x2 dot. We have found the x1 dot. So we know the x1 dot. What is your x1 dot? It is simply x2, right? And you have to found the x2 dot. So what will be your x2 dot? x2 is this. So this dot is again the first derivative of this omega. That will give you this thing, the second derivative of this delta, right? Because look, from where you got this thing? From this, right? This was your second step variable. So if you again do the first derivative of this thing, you will again get this thing, right? So this is simply, you have to take these two terms to the right side. So minus this, okay? And now this is replaced by x2, and this is nothing but your x2, okay? So you can just write your x2 dot is this minus pi f naught t over t is x2 minus pi f naught ps over t is x2, okay? You have to represent your x1 dot and your x2 dot with respect to your x1 and x2, because in your general expression it will be x dot multiplied by equals to a multiplied by x, and inside x we will have the x1 and x2, right? So that's why somehow we have to represent your x1 dot and x2 dot with respect to the x1 and x2, so that you can just write this general expression. Have you got the idea? Now this is equation number 1, this is equation number 2. Now you have to form the matrix. So the left side will be x dot, that is x1 dot x2 dot, okay? What is your x1 dot? It is simply x2. So you know the x, so just first fill up this x1 and x2, okay? Then you have the a, so you have to find out the size of the a. Look, this is 2 by 1, this x is 2 by 1. So what is the size of a? It will be 2 by 2, right? So that the product can be 2 by 1. That will match the left side size, okay? Now what will be the, now look at the first row, because this first row will be multiplied by x1 and x2 respectively, and that will give you the x1 dot, right? So look, 0, there is no x1 term here, right? That's why, so you can write your x1 dot, this thing, the equation number 1, I can rewrite it like 0 multiplied by x1 plus 1 multiplied by x2, right? That's why there is 0 and there is 1 here, okay? And for the x2 dot, look, this multiplied by x1, so this second term is here, look, with ps, and this t multiplied by x2, so this d term is here, that will be multiplied by this x2, and you will get the x2 dot, okay? Have you got the idea? Now do we need to introduce the pu term here? We can introduce, but these two will be 0, because look, we have already got the x1 dot and the x2 dot from the ax expression. we have the look, there is no BU term. That means we do not have any input for this system. And this expression can be written as x dot equals to simply ax. And there is no BU term, right? And this form is called the homogeneous state equation. So this is called the homogeneous state equation. There is another name of this thing. It is called the unforced state variable equation. Why unforced? Because there is no u. U means forcing function, right? Yes, so here, what is the interpretation of u or the input? It is actually the forcing function. So there is no forcing function here present in this system. That's why this is called the unforced state variable equation. Okay. How the system can work without any forcing function, without any excitation system? That we can, that thing or that actually conclusions we can be clear from this example. Okay. Let's say this is our system, this is the AC input, and we have R, L, and C. Let's say in the first case, before time t equals to 0, there was no stored charge inside the L and C. So now the system can't operate without this VA, right? Let's say at time t equals to 2, the switch is closed. So now the current is flowing, the system is working. Okay. Now there will be some charge inside this thing. Right? Okay. Now if you remove this input, can this system work? It can work now, right? Because there are enough amount of stored charge inside this L and C, right? So we can say that without this forcing function or without this excitation system, our system can also work, right? And this behavior is called, okay, so whenever there is the input present in the system, that behavior is called the forced response. In your circuit 2 course, we have learned about this type of responses, right? And whenever there is no excitation, that response is called the natural response. Okay, so this is called the natural response or the unforced response. Okay, the same thing has happened here. There is no excitation. That means the system or the behavior is called the unforced behavior or the natural behavior. Okay. So for the linearized single machine infinite bus system, we have modeled our system in the state space model, right? So this is x dot, this is a and x. So do you have any conclusion up to now? So with this, we will just, so this is our input equations, right? As well as you can formulate the output expression. Okay. So actually I want to conclude here because the previous section I have completed up this slide. Okay. So in the next class we will start from this slide number 3. Okay. So have you got the idea? Have you got the background concept of this topic? This modeling.
স্যার তার মানে ইনপুট থাকলে হচ্ছে we will get BU, but if there is no input then BU is explained.
Because look, without this BU, you are already getting the expression of x1 dot and x2. So there is no way to introduce this. So no input or no forcing function means this is unforced behavior. Okay, so you have to understand this thing very well. Okay, so if you have any conclusions, you can ask the questions now or in the next class as well. Because in the next class, in tomorrow's class, I